Hello, everybody. How are you? Are you ready for some serious fun? Woohoo! So, welcome to my session about latches, spin locks, and lock-free data structures. Who of you knows latches, spin locks, lock-free data structures? Perfect. Trust me, it will change over the next 2 hours. Few words about my person. My name is Klaus Aschenbrenner. I come from Vienna in Austria. As I'm always saying in the States, we have no kangaroos. So Austria is not Australia. I'm the CEO and founder of the company SQL Passion. With that company, I'm providing SQL Server consultancy and training services across Europe. I'm an international speaker, author and blogger, means I'm traveling around the whole year talking about crazy things in SQL Server, like these days here in Copenhagen. Tomorrow afternoon I will fly to London to the SQL Bits conference where I'm also presenting 2 sessions about SQL Server. I'm also a Microsoft Certified Master for SQL Server, which doesn't matter anymore because Microsoft just retired that certification because they have made no profit out of it. I've also written the book Pro SQL Server Service Broker. Who of you knows Service Broker? Almost nobody. Service Broker is an asynchronous messaging framework that Microsoft first introduced back with SQL Server 2005. And with Service Broker, you can write asynchronous, scalable database applications. So as you can already see, I'm just working with things that nobody cares about. No, just kidding. You can also follow me on Twitter, and you will also find a huge amount of free information around SQL Server on my SQL Passion Academy, where you find a free newsletter where I'm spamming you every week with performance-related topic. And if you're really crazy, you can also watch my YouTube channel where I'm providing every month a so-called SQL Server Quickie. Who of you knows SQL Server Quickies? It's safe for work. So I'm not providing here porn or anything else, just a short video about a specific performance-related topic in SQL Server. First of all, this is a very, very deep dive session, so I'm not talking very, very high level like 0.0 or so. I'm really talking about low-level stuff, about what happening inside SQL Server, how SQL Server synchronizes access to our databases when we are working with multiple concurrent users in SQL Server. We have 2 hours. Maybe I'm making a break of 15 minutes. Let's see. Also depends on you. If you need a break to back off from that intensive content, if you don't need a break, we can continue. It's up to you. As the title already implies, I'm talking about 3 different synchronization things in SQL Server. I assume that everybody already knows locking and blocking in SQL Server, so I'm not talking about locking, blocking, deadlocking. I will just show you what happens underneath in SQL Server on the physical level, how SQL Server implements and synchronizes our users. So the first part of this session is about latches, which are just low-level synchronization objects in SQL Server. I want to show you some specific scenarios where you can hit performance problems with latches in SQL Server, how you can troubleshoot and finally resolve them. Then we move on to so-called Spinlocks. Spinlocks are just more deep dive concepts in SQL Server. So Spinlocks are just used underneath the level of latches. And finally, I will talk about lock-free data structures in SQL Server, which SQL Server initially implements with SQL Server 2014 in memory OLTP, which was codenamed Hackathon in the past. So that's our main agenda for the next 2 hours. Let's talk in the first step about latches. Every one of you hopefully already knows about locking and blocking in SQL Server. Means when we run transactions in SQL Server has to isolate these transactions from each other. When we are talking about databases, we have readers, our select statements which are reading data, and on the other hand we have writers which are changing our data with insert, update and delete statements. And those two kinds of operations, activities, SQL Server has to isolate from each other. In the context of SQL Server, on the logical level, SQL Server acquires for select statement for read operations a so-called shared lock, and when we are changing data, SQL Server has to acquire an exclusive lock. The bad thing about exclusive locks is that an exclusive lock is not compatible with anything else in SQL Server. Means when you have an exclusive lock on a record, you can't concurrently read that record because a shared lock isn't compatible with an exclusive lock. When you are currently reading a record, you can't change that record, and when you are changing the record, you can't change at the same time the same record because a writer blocks a writer. Means as soon as you are having an exclusive lock on a record or on a page or even on a table, it leads to blocking situations, and if things are going really badly and crazy, it can also end up in a deadlock situation. SQL Server just uses locks on the logical level. Means when we are starting our transaction, SQL Server acquires these locks. Finally, when we are ending that transaction with a commit or rollback, SQL Server releases these locks. The nice thing about locks is also that we can control locks. So every time when we run a transaction in SQL Server, we can specify with the transaction isolation level, with uncommitted, with committed, with biddable, with and serializable, how long readers, select statements are holding their shared locks. When we are talking now about latches, things are getting more complicated because we can't control latches directly. Means when we are running a transaction in SQL Server, there is nothing like a latch isolation level in SQL Server. Means we can't control directly how long latches are held by SQL Server. We have to trust SQL Server, which is sometimes a bad idea. Okay? So a latch itself is just a light-wide synchronization object. Light-wide means that SQL Server just acquires latches in some specific points in time when we access shared resources. For example, when we have a page in memory, a page in SQL Server is always a unit of 8 kilobytes. When we have that page in memory, in the so-called buffer pool, and we are reading that page from the buffer pool, then SQL Server has to acquire a shared latch on that page. Means nobody else can change that page in memory concurrently. Because when we are changing a page in memory, for example, when we're performing an update statement, then SQL Server acquires an exclusive latch on that page in memory. Means when you want to read and write to a page in memory concurrently at the same point in time, you are leading to a locking and blocking situation in main memory. Who of you has attended yesterday's the pre-con yesterday from Brent Ozer? A lot of us. Perfect. Brent has lied to us. Don't tweet that, otherwise he kill me. Brent has lied to us. Brent has told us we can improve our performance very easily. We buy RAM. The more the better. I will show you today with a huge amount of RAM, you can also lead into blocking situations in main memory. Imagine that yesterday we have seen, for example, a page IO latch shared, means we are waiting on our slow storage. Today, I will show you page latches, means we are waiting on accessing pages in main memory. Just think about that. Blocking situations in main memory, where we have learned yesterday that we have latency times of nanoseconds. Even with that short latency time, you can also lead to blocking situations. So that's very, very important. Latches in SQL Server are just used for thread synchronization. As I've already said, when we are reading a shared resource from main memory, when we are writing to a shared resource to main memory, these read and writes can't happen at the same point in time, because otherwise you would have a dirty read in main memory. So SQL Server just uses those latches for the thread synchronization. As we will see also later, SQL Server has other shared data structures which SQL Server has to protect, for example, the log manager. When we write to the transaction log, writing to the transaction log is just single-threaded, means SQL Server can be only as fast as the transaction log. Means when you have a slow storage where you put your transaction log on, your SQL Server will be also slow. And as we will see later, the transaction log is guarded by a latch in SQL Server, by a specific one. Okay? And as I have already said, the bad thing about latches is we have to trust Microsoft that they have not introduced any bugs. We have no way to control latches directly in SQL Server because there is nothing like a latch isolation level. Okay, so that's very, very important. I'm also comparing here locks versus latches. When we just look on a few things, as we have already said, with locks, we control transactions on the logical level. With latches, SQL Server controls and synchronizes threads on the physical level. Locks are always held during the entire transaction. As we will see later when we are talking about latches, a latch is just acquired for a very, very short amount of time. Okay? Also very, very important, deadlocks. When we are talking about locks, we have the deadlock monitor, which is just a background process in SQL Server which runs every few seconds, goes to the lock manager and checks the internal lock table if we have a deadlock situation. If yes, the cheapest transaction is chosen as the deadlock victim and the transaction is just rolled back. When we are talking about latches, there is nothing like a dead latch detection. When you have a dead latch in SQL Server, you can be happy because you have found a bug in SQL Server. The bad thing about your happiness is both threads will wait forever. Okay? Shouldn't occur normally. Let's talk about the various types of latches that we have in SQL Server. We have three types of latches. We have so-called buffer latches. Buffer latches are used in SQL Server when we read and write pages from and to the buffer pool in SQL Server. Means every time when we read a page from the buffer pool, SQL Server latches that page with a shared latch. Every time when we write to that page, SQL Server acquires an exclusive latch. And the same thing as with locking in SQL Server, both are incompatible to each other. Means you can't read and write to the same page at the same point in time in the buffer pool of SQL Server. We have also so-called page IO latches. I think every one of you has already seen them, because normally we have just slow storage. Means when a query requests some data, during its execution and that data is currently not cached in the buffer pool, then the buffer manager goes out to the storage and reads those pages from our slow storage into the buffer pool, and in the meantime SQL Server reports a page IO latch shared wait type. Means every time when you are waiting on your slow storage, SQL Server reports page IO latches. And the third kind of latches that SQL Server implements are so-called non-buffer latches, and those are latches which are used by SQL Server to protect shared data structures, like the log manager when we are writing out to the transaction log. And the nice thing is, in SQL Server, that SQL Server keeps track on all three levels when we are waiting on those specific latches. For example, when we are talking about buffer latches, we can go to our wait statistics, SysTMOS wait stats, and SQL Server tells us how often and how long we have waited on page latches when we have accessed our buffer manager. As you can see here, we have a page latch null latch, a keep latch, shared latch, update latch, exclusive latch, and destroy latch. As you can see from the wait type name, there is no IO in its name. Means it's a wait type that occurs in main memory. Main memory which is very, very fast, or it seems to be. Okay. We have the IO latches. You can also see those IO latches in the wait stats, in SysTMOS wait stats. Again, we have a page IO latch, null latch, keep latch, shared, update, exclusive, and destroy latch. Means we're just waiting on our slow storage. Those are normally the latches that you are working every day when you are troubleshooting your queries, when you want to find out why a query is slow. Normally you will see a page IO latch shared because by definition we have bad indexing strategies, means SQL Server has to read a huge amount of data from our storage, and this takes some time, and in the meantime SQL Server reports an IO latch as a wait type back to us. And in addition we have those non-buffer latches, and the nice thing here is that SQL Server provides us a detailed breakdown in SysTMOS latch stats on which specific non-buffer latch we have waited in SQL Server. For example, you can find out with those latches how long your queries were waiting on the autograph operation of the transaction log. Because every time when the autograph operation on the transaction log kicks in, SQL Server acquires a latch, and when the autograph of the transaction log is completed, then SQL Server releases that latch, and in the meantime we will see on that specific latch the wait time. I will show you that afterwards. Let's have a look on that. Just a very simple demo, just 3 select statements, nothing more. So as you can see here, the first step we have our buffer latches, SysTMOS wait stats. So those are the waiting times that occurs when we read and write from the buffer pool in SQL Server. I have restarted my SQL Server, so currently no waiting has occurred. As you will see later, this will change. So again, we can see how often a specific task, a thread in SQL Server has waited on that specific buffer latch, how long the waiting time was, our maximum waiting time, and the time that we have spent in the runnable state, in the signal state. That's also very, very important. When we are talking about latches, then we also have to say that SQL Server puts, or that the query which is waiting on that latch goes through the complete query lifecycle. Query lifecycle in SQL Server consists of 3 different states: the running state, the suspended state and the runnable state. Means we are running in a running state until we acquire a latch, which we can't currently acquire, and after that, SQL Server puts that query into the suspended state. And in the suspended state, we have to wait until we can acquire that latch. Afterwards, SQL Server puts us from the suspended state into the runnable state, and in the runnable state, we have to wait until a CPU becomes available so that SQL Server can put ourselves back on the CPU in the running state. Means every time when we wait on a latch, our query goes through that query life cycle. This means, as a conclusion, that SQL Server protects data structures with a latch where we are expecting high or long waiting times. This will change when we talk afterwards about Spinlocks. A Spinlock is a so-called busy wait, means we're just waiting actively on the CPU. Internally, SQL Server or the query just spins in a while loop until we can acquire that Spinlock. So it's a busy wait. A latch isn't a busy wait because SQL Server puts that query off the CPU when we are waiting on that latch. Okay? We have here our page I/O latches that you should already know. For example, we have here the page latch shared when we are reading data from our slow storage, page latch exclusive when we are writing out data to our slow storage, for example, through the lazy writer or checkpoint process in SQL Server. And finally, we have in SystemOS wait stats also the non-buffer latches. So SQL Server just tells us here with the wait statistics how long we were waiting on non-buffer latches. The problem is SQL Server consists internally of hundreds of different non-buffer latches, means we have no idea on the wait statistics how long we have waited on a specific non-buffer latch, and therefore we have a second dynamic management view, SystemOS latch stats, and within that dynamic management view, SQL Server gives us back the waiting times for every individual non-buffer latch in SQL Server. And as you can see here, when we go down, we have here on SQL Server 2014 RTM version 163 non-buffer latches. Okay? Means on the RTM version of SQL Server 2014, we have 163 different shared data structures which are protected by a non-buffer latch. You will see later why I'm using the RTM version of SQL Server 2014, because I need a specific bug. Okay? Questions on that? Who can follow me? Perfect. Now you say, okay, that's nice, but who cares about latches? Every one of us should care about latches. Let's talk in the first step about clustered indexes. What's the recommended clustered key value in a clustered index when we follow all the best practices? It should be static, so it should not change because the clustered key value is also the logical lookup value in our or in all our non-clustered indexes. It should be very, very small, and it should be ever increasing, like an int identity value. Means when we create a clustered index on an int identity value, we always insert records at the very end of our clustered index, because our int identity value just gets higher and higher and higher. Make sense? The advantages: we have no index fragmentation. We make Paul Wendell very, very happy. No index fragmentation. The bad thing about that best practice is it doesn't scale in any way, because of the latches that SQL Server internally has to acquire when we insert records at the very end of that clustered index. As I've already said, when we change a page in the buffer pool of SQL Server has to latch that page with an exclusive latch. Means when we insert a record at that very end in the clustered index, nobody else can read from that page at the same point in time, and nobody else can make other inserts at that clustered index. Mainly, you have single-threaded inserts at the end of your clustered index, because that last page gets a hotspot. Make sense? What can you do to overcome that problem? Any ideas? Yeah? Yeah, you can fit less pages on a single, or less rows on a single page. Because in that scenario, the smaller your records are, the worse your performance problem will be. And the idea of a good database design is to have very, very small records so that you can fit a huge amount of data on a page. You can solve that problem very, very easily to make sure that only one record is stored on one page. Just pad that record with a character column and make sure that the record is a little bit more than 4,400 bytes long. Very simple. Other ideas how we can change that problem? A unique identifier. Yeah. Unique identifier, a very, very bad and good idea. Let's talk about the bad things in the first step. It's bad because it leads to index fragmentation. We have a huge lookup value in our non-clustered indexes, 16 bytes versus 4 bytes. And the nice thing, with a unique identifier, we are getting unique values. Means when we are using a unique identifier, we are just spreading and distributing our inserts across the whole leaf level of that clustered index. Means we get concurrency. Yeah? We can also make table partitioning. The problem with table partitioning is you need the expensive edition of SQL Server, Enterprise Edition. Then you should also use the expensive edition, because otherwise you have other problems. And the other problem is that partition elimination doesn't really work anymore, because you are partitioning on a hash value. Third option that we have, we can use in-memory OLTP that was introduced with SQL Server 2014. But in-memory OLTP, also not really a good thing, because it's just a version 1. Almost nothing works. No, for ring keys, we can't change our tables. We can't do almost nothing. Just insert records. Yeah, we can reverse the key. For example, Oracle is doing that. That's also a way. Also with some other side effects. Let's have a look on that specific problem in SQL Server. I'm just waiting a few more seconds. I'm just creating here a new database. Nothing special about that. And I create a new orders table. We're just following here all the best practices. So we have an order ID column, an int identity column, we specify our primary key constraint, and we are telling SQL Server that the primary key constraint should be enforced by a unique clustered index, which is by default the case. If you create that table, you have scalability problems. You have single-threaded inserts at the very end of that clustered index. That last page insert latch contention that I have demonstrated earlier on the slide. To give you an idea what this means, I create here a simple stored procedure. Nothing special. In a while loop, I like while loops. In a while loop, I'm just inserting 10,000 records. Just 10,000 inserts with an ever-increasing key value means we're just inserting at the very end of our clustered index. So let's create that. And let's clear the wait stats. You should not do that in production because you are losing everything regarding your waiting time. So you have no idea why SQL Server wasn't performing very good in the past. Just want to show you here by clearing the wait stats how much wait we accumulate when we are executing that stored procedure. And I'm executing that stored procedure not with one user. No, I'm executing that stored procedure with 100 users because we want to have parallelism across multiple users, because with one user you can't have any latch contention because only one user just inserts records at the very end. But with 100 concurrent users, things are changing. I'm using here the tool ostress.exe, and you can download that from Microsoft from the so-called RML utilities. It's a free download, doesn't cost you anything, and I have here now a simple command line. I'm connecting to my named instance, SQL Server 2014. I'm specified that specific stored procedure in that database that we have created, and I specify that I want to execute that stored procedure across 100 concurrent users. Let's copy that over to the command line prompt and execute it. Let's open Activity Monitor. And what I'm also showing you now, we can go to system exec requests, where session ID larger than 50. And we have here 101 connections. Our connection and the 100 users. And as you can see, almost every connection, every session is in the suspended state. It just waits. And we are waiting on a page latch exclusive. No I/O involved, we are just waiting to access the last page in that clustered index to make the insertion of that record. So you can see 101 rows. When I run that again, you can see here from the state, almost everything is in the suspended state. When we go to the activity monitor, you can see waiting tasks, 98. Single-threaded inserts at the end of our perfect clustered index. Just think about that. Of course, when you have such a problem with your orders table, you're a really happy person because your business goes very, very well. But just think about logging, auditing tables. I know customers, or I'm dealing with customers, they have websites. and they have to log every mouse click that we as end users are doing. Just think about that. In such a case, an ever-increasing clustered key value doesn't really scale. We are finished, and as you can see from the output of ostress.exe, 1 minute 33 seconds. To just insert 10,000 records across 100 users. 1 million records. Wow. SQL Server is slow. Let's move to Oracle. No, just kidding. I can prove you that we have really inserted 1 million of records, so I'm not fooling you here in any way. Just 1 million records. Okay? Question? When you have two concurrent inserts, one is waiting. Very simple. Imagine we have here a toilet with just one room, just one resource. As soon as two persons are going at the same time to that toilet, the first one wins, because the first one acquires an exclusive latch and closes that and locks that toilet. Okay? I will talk later in a little bit more detail about the public toilet of SQL Server, DempDB. Question? No, we are just waiting until the previous transaction has inserted that record on that page, and then the previous transaction releases that exclusive latch, and now we can acquire that exclusive latch. So it's just a wait in the main memory. Okay? We are not waiting for the entire transaction. On the entire transaction, we have an exclusive lock on that record. But here we have a latch for that amount of time when we want to write that to that page in main memory. So when you want to write to those individual memory cells. It's on the physical level. Okay? The nice thing about it is that SQL Server tells you how long we have waited on specific latches on the object level, on the table level. We have here one dynamic management function, system_db index operational stats, and within that DMV you have two columns, page latch wait count and page latch wait in milliseconds. So SQL Server is telling you how long we have waited on those page latches for a specific table. So you can provide here database ID, object ID, index ID, partition ID. So let's run that. And as you can see, on average, we have waited 4 milliseconds. And that guy from Chicago told us yesterday main memory is so fast. That's not the truth. Just think about that. 4 milliseconds. Our SSD disks are faster when you're doing it in the right way. Okay, just think about that. On average, we have waited 4 milliseconds until a transaction or a thread in SQL Server could have acquired that latch to make the insert at the very end of our clustered index. We can also see those waiting times from our wait stats. So as you can see, we have a huge amount of shared latches when we want to read that page, and we have a huge amount of exclusive latches when we want to write to those pages. Of course, here from the wait stats, we have no idea which pages SQL Server has waited here on. Okay? So let's try to solve that problem. Now you are not allowed to tweet anything. Let's create a table and enforce the primary key constraint with a unique identifier. Ouch. On one side, but as you will see, this approach scales. Let's create that table. Let's create another stored procedure. Again, 10,000 inserts in a while loop. Now we generate our random clustered key value. So we are asking SQL Server for 99% index fragmentation that we will also get. Whoops. And we clear again our weight stats. What we can do, I copy out the old ones so that we can compare them later. So let's clear them. And let's run again that stored procedure with 100 parallel users. So again, we're just inserting 1,000,000 of rows into that table. We're doing the same amount of work as previously. Our baseline, 1.5 minutes that we want to beat. As you can see from Activity Monitor, we still have weights, but the weights were not really high. And as you can see, we're already finished. Let's make that larger, it's easier. Oops. Those are 6 seconds. Nice, isn't it? 6 seconds versus 1.5 minutes. Just think about that. Amazing. Because we have just distributed our inserts across the whole leaf level of the clustered index. Means SQL Server just accessing different pages at the same time, and SQL Server latches different pages with an exclusive latch. Means we have improved the throughput, the concurrency, and the scalability of that specific workload. I'm not fooling you here. So again, we have just 1,000,000 of rows. Okay? Same amount of rows that we have inserted. And when we look on our weight stats, I copied them out to Notepad. You can also see they are lower. For example, earlier we had around 410,000 tasks which were waiting on a page latch shared. Currently, 127,000 times. Page latch exclusive that we needed for the insertion of a records, 1.3 million with an int identity value, with an ever-increasing clustered key value. With our unique identifier, we have only waited 4,000 times. Just think about that. So very easy to prove that a random clustered key value scales. But this doesn't mean that you're going home and drop all your clustered indexes and generate unique identifier values. That's not the goal. You only have to think about such crazy solutions when you have those specific problems. So it doesn't make sense to create a random clustered key value on every possible table. Only on those tables where you have that specific problem, that last page insert latch contention. That's also very important. Okay? But you can see with different techniques, we are getting different throughput. Of course, here in that table, we have an index fragmentation of nearly 100%. Means when we are doing a clustered index scan, it leads to random I/O in our storage when we have to read those pages from the storage into the buffer pool. So there are also side effects. Okay? Questions on that? Yeah. The row lock, but the row lock is just on the row. Here we are talking about the latch, which SQL Server places on the individual page. It's on the physical level. While you can concurrently do inserts, because SQL Server acquires an exclusive lock on the row and an indent exclusive lock on the page. And an indent exclusive lock is compatible with an indent exclusive lock. That's the problem. I think SQL Server has introduced page level locking in SQL Server 7.0, and this was also the time when they have introduced the page latches. Because earlier, before SQL Server 7.0, this wasn't really a problem. I have no idea how SQL Server has done locking these days, because at that point in time I went to school and learned other crazy things that I didn't care about it. But in the older days, you had no way to concurrently make an insert because the lock already blocked you. But since SQL Server 7.0, we have the page level locking, means SQL Server acquires an indent exclusive lock on the page, and as I've said, an indent exclusive lock is compatible with an indent exclusive lock. Means the lock itself wouldn't block you, and therefore we have the latches on the page. Means we are waiting in main memory of SQL Server. Other questions? Are you already impressed? Yes? No? Perfect. Later on, when we are talking about lock-free data structures, we will continue with that example, and I will show you how we can finally also resolve that last page insert latch contention within memory OLTP. So those 6 seconds is not our final throughput that we have here. But we have already made a huge step from 1 minute 30 seconds to 6 seconds. Another common problem where you are dealing with latches is in the public toilet of SQL Server. What is the public toilet of SQL Server? DempDB, because every happens in DempDB. The word S-H-I-T. When you run DempDB with a default configuration, you will have a so-called DempDB latch contention. Default configuration means with just one data file. Who runs DempDB with one data file? Come on, nobody sees us. Sorry? Okay. Or who knows? Let's rephrase the question. Who knows SQL servers which are running with just one data file in DempDB? Everyone. Okay, perfect. So when you know such a SQL server, you can go to that DBA and you can tell him, hey, I have some problems in my DempDB configuration because the default configuration of DempDB doesn't really work. We are using DempDB for creating temporary objects, like temp tables, table variables. A table variable is also persisted in DempDB. Microsoft just fools us here. It's a variable persisted in DempDB, with the side effect that we have no statistics. Means when we persist data in DempDB, then SQL Server has to find in the first step some free space. And to keep track of that free space, SQL Server uses internally some specialized system pages. A so-called SGAM page, Shared Global Allocation Map page, a so-called GAM page, Global Allocation Map page, and a so-called BFS page, Page Free Space Page. Crazy words. Means, when you create a temp table and you insert a record into that temp table, then SQL Server goes to that specialized system pages, reads that page, finds a free space, uses that free space, and afterwards SQL Server updates that specialized system page to make a modification to say that free space is now occupied. Means when we are reading from that system page, SQL Server has to acquire a shared latch. When we make the modification on that system page, SQL Server acquires an exclusive latch. So we have the same thing as in our clustered index. One query can only make at any point in time one change on such a system page. How can we resolve that latch contention in DempDB? Very easy. We just provide additional data files. Because with additional data files, we have multiple copies of those specialized system pages. Because every data file has those specialized system pages. Means SQL Server implements a so-called round-robin allocation. Means the first 64K of data are allocated in the first file, the second in the second file, the third, for example, in the first one, second one, and so forth and so on. Just a round-robin allocation means we can distribute our load, our workload across multiple files. The recommendation that Microsoft has made here in the past is that we should have a one-to-one mapping between DempDB data files and CPU cores. This doesn't hold true anymore because we can have a huge amount of CPU cores. Therefore, the recommendation is when you have up to 8 cores, you just give DempDB as much data files as you have CPU cores, and afterwards it just depends. You have to benchmark it for your specific workload, around 1/2 to 1/4 of data files as you have CPU cores. Let's have a look on that specific problem. I have here a default configuration of DempDB. So as you can see, I have just one data file, one transaction log. The only thing that I have changed here is the initial size. Everything else is just a stupid, silly default configuration. Okay? Just one data file, and as you can see, I'm running here on a Mac with four cores in my virtual machine. Okay. So let's create a new database. And I create again a very simple stored procedure. I'm not really doing complex things. Just a few simple things. Inside that stored procedure, we create a temp table. We create a unique clustered index on that temp table, on the first column. I'm inserting 10 records into that temp table. Afterwards, I create another stored procedure, and in a while loop, as I've already said, I like while loops, I'm just calling that stored procedure 100 times. Nothing special here. Let's execute it. perfect, query executed successfully. Let's deploy it to production. But in production, things are a little bit different. We are dealing with multiple users, hopefully. If not, change the single user mode to multiple user mode. Again, we're just stress testing this specific stored procedure with 100 parallel users. So we want to know how that stored procedure scales when we execute it concurrently with 100 parallel users. So let's do that. As you can see from Activity Monitor, immediately we have again around 100 waiting time, 100 waiting tasks. Means that stored procedure is just, or the creation of the temp table is just done serially, single-threaded in SQL Server. When we go to SysTMOS waiting tasks, and when we restrict on those specialized system pages, you can see we have here 95 waiting tasks. Now we are finished. The whole workload took around 33 seconds. Okay? As you can see from Activity Monitor, very, very nicely, we had those waiting tasks almost the whole time during that execution. Just a latch contention in the public toilet of SQL Server. How can we solve that? We have two options, three options. The first option is for DBAs. We are just changing the configuration of TempDB. We can also look into the wait stats. I copy that again out. Oops. And you can see here we have again a huge amount of page latches. Of course, here from the output of the DMV you have no idea if this belongs to TempDB or something else. We know it belongs to TempDB because nothing else was executed on that machine in the meantime. Okay, so as you can see, page latch update 283,000 times, page latch shared 730,000 times, page latch exclusive around 100,000 times. So a huge amount of page latches on which we were waiting on. Let's clear them again. And in the next step, we're just reconfiguring TempDB. We're not changing our workload in any way. In the first step, you should give TempDB a reasonable size. I think the default size is 8 megabytes. Who has already seen a TempDB of 8 megabytes in production? You are not doing serious stuff with SQL Server. So when you see that your TempDB needs 10 gigs, then reconfigure your TempDB for 10 gigabytes. Because when you're restarting SQL Server, then SQL Server resets TempDB to the default configuration of the model database. So again, your TempDB has to autogrowth over the time. So it's always a good best practice to change the initial file size. Means in our case, when we are restarting SQL Server, our data file has 512 megabytes. Question? Of course, the log file is also another story. Also a stupid default configuration. I'm just talking here today about the data file. And now I'm just giving TempDB an additional file. Just one additional file. When you have multiple files in TempDB or also in a user database, you have to make sure that both or all files have the same time, same size. Because SQL Server makes sure that all the files are full at the same time. Imagine we have one file with 1 gigabyte and another file with 500 megabytes. In that case, SQL Server makes 2 allocations in the large file, 1 allocation in the small file, 2 allocations in the large one, 1 allocation in the small one, to make sure that both are full at the same point in time. So, in our case, we have now a DempDB configuration of 2 files. Both files have the same size. Are we already finished? Come on, yes or no? Why not, Edge? Well, I'm just trying it with 2. I don't have too much time. But yeah, best practice, 4 files. Yeah? Autograph should be the same, yeah? I will talk about that later. The problem that we have currently is that we have already executed some workload. Means we have already written to the first file, and the second file is empty. So they have different sizes currently. Means our I/O is currently not really balanced, because the second new file is accessed more as the first old file. So you have 2 ways to deal with that problem: add more files, or do restart SQL Server. Yes, restart SQL Server. I do the easy option. I'm just restarting SQL Server. Should we make a break? No. Perfect. Well, no answer means no. No problem. Of course, you are not my hostiles. You're always able to leave when you want. So we have restarted SQL Server. As you can see, no, you can't see it here. Let's go to Files. We have now the configuration that we have specified earlier. So when we're restarting SQL Server now, DempDB has in our case 1 gigabyte of file size. So those configuration changes that we are making in DempDB, those are persisted across SQL Server restarts. Okay? So in the next step, we just execute our workload again. As you can see, previously it took around 33 seconds. Now we have added 1 additional data file to DempDB, means we have made a change. So we are just rerunning our workload again, and we make sure, or we check if that change was a good or bad one. That's also very, very important. When you make some changes in SQL Server, don't make too much changes at all. Just 1 change after 1 change. When you have made a change, just measure your performance, your throughput again. And as you can see, even on crappy Mac hardware, we improved our performance by 30%. 22 seconds versus 33. Just 1 additional data file. Of course, when I'm adding here a 3rd, 4th data file, performance will get better, but not too much. So we are making large steps at the first place, and afterwards minor steps and minor steps. Okay? So that's the first change that you should always make in DempDB. Just give DempDB more data files to overcome that latch contention in DempDB. That's very, very important. I always see that when I'm performing SQL Server health checks, that sometimes people are just running with the default configuration of DempDB. Doesn't really scale in any way. Okay? Yeah. or as I've already said earlier, you just add more additional files, then you have also the rebalancing between the newly added files. What was the question? No, just kidding. The question was, the question was if we always have to restart SQL Server. No, we don't always have to restart SQL Server. As I've already said earlier, you can also just add more additional files, and then the I/O will be balanced across those newly added files. Of course, when you have just one file and you add one additional file and you had already a workload that used tempdb, then the new upcoming workload will just hit the newly added file because it's an empty one. Make sense? Other questions? Perfect. So changing tempdb, just one thing, one change that we can do transparently as DBAs. In the next step, we can also talk to our enemies, to our developers. Developers also have a really huge influence how SQL Server will use tempdb. SQL Server is able to reuse cached tables, temp tables in tempdb. There's a blog posting by Paul White, which is a really crazy guy from New Zealand, crazy in the positive sense. And Paul just describes in that blog posting how that temp table caching in tempdb works. When you read that, you need a huge amount of coffee. Or alcohol, no. Coffee is always better. A caching of a temp table is only possible in some specific scenarios. For example, when you have a stored procedure and you have inside that stored procedure TTL statements, SQL Server can't cache that temp table. Imagine you are creating a stored procedure and afterwards you are creating all your indexes on that temp table. In that case, SQL Server can't cache that temp table because you're just mixing TML with TTL statements. So let's have a look on that. We have in system OS performance counters a performance counter called temp tables creation weight. Means that performance counter tells us how often SQL Server creates a temp table. So what I'm doing here, I'm just grabbing that performance counter. I'm executing my stored procedure. I'm grabbing that performance counter again. And I'm just doing a subtraction to see how often we have created a temp table. So it's very easy in a development environment where you are the one and only user to see if SQL Server is able to cache that temp table that you have created in your specific workload. And guess what? As you can see, we have created here in that test 1,000 individual temp tables in tempdb. Means SQL Server had to access 1,000 times those specialized system pages. Why? You have already seen the answer. Otherwise the question wouldn't be fair. Let's go up to our stored procedure definition, if we find it. We have created a temp table, and afterwards we have created a unique clustered index. Means we have in our stored procedure a TTL statement, means SQL Server is not able to cache that temp table anymore. how can we get rid of that unique clustered index creation statement? Create a primary key constraint. So what I'm doing in the next step, I'm changing my stored procedure. And now I'm enforcing that unique clustered index just with a primary key constraint. Means the outcome is the same, but now we have no DDL statement in our stored procedure anymore. Means SQL Server is able to cache that temp table. So we just create that temp table once, we access those specialized system pages once, and afterwards we're just reusing it. So let's make that change. When we check the perfmon counter again, we have just created one temp table instead of 1000. So SQL Server is now able to cache and reuse that temp table. Yeah? No? I think so, yeah. So a drop table should also influence it, yeah. But you don't need to drop the temp table because it's out of scope as soon as the stored procedure finished its execution. So that's a really nasty thing in SQL Server. As soon as you have a DDL statement like a create index, non-clustered, clustered index, SQL Server can't cache it anymore. The nice thing in SQL Server 2014, we are also able to create non-clustered indexes inline during the table definition. That's just a syntax that is needed for in-memory OLTP. Means when you create your table, when we go up, when you create your table, you can also create here your index. That's nice. Question? The question was how long that temp table is persisted. Answer, please read Paul White's blog posting. I haven't currently it in my buffer pool. So, what we do now, I'm clearing again my wait stats, and I'm rerunning my workload. As you can see, currently, or previously, we needed 22 seconds with 2 data files in TempDB. So let's rerun that workload again, and now it should be hopefully faster. Let's see. Yep. 12 seconds. Just think about that. 10 seconds improvement just by making a simple change to that stored procedure. The question was if you need 2 TempDB files. In that case, not really. I haven't tested it the other way, I have to check that. But it's still a good recommendation to have multiple data files, because as soon as you have a create or as soon as you have a DDL statement, you hit the same problem. But you are right, you can also do that demonstration the other way around. Okay? So as you can see, TempDB is always a performance bottleneck by design. So we were able to improve that specific workload from 33 seconds down to just 12 seconds. Impressive, isn't it? Perfect. Okay. If nothing helps, you can also drop TempDB. No, just kidding. When you are losing TempDB, you have lost your SQL Server. There is just one specific trace flag, 1118, which isn't really needed anymore. It was needed on SQL Server 2005, but since SQL Server 2008, it's not really needed anymore. When you enable that trace flag, then SQL Server doesn't need to access those SCAM pages anymore, shared global allocation map pages, because SQL Server initially creates all our database objects in a so-called uniform extent, means our table is at least 64 kilobytes large. I've just mentioned that trace flag for completeness when you see it somewhere, but as I've said, since SQL Server 2008, it's not really needed anymore. Questions on the DempDB stuff? Are you still awake? Perfect. I want to show you another example about latches. The auto-growing of the transaction log. Not who relies on the auto-growing of the transaction log. Who knows a database where the transaction log auto-grows? Everyone. Let's see why the auto-growth of the transaction log is very, very bad. The biggest problem that we have with the transaction log in SQL Server is that SQL Server writes the transaction log just sequentially. Means when you provide SQL Server multiple transaction log files, which is possible, then SQL Server writes to the first one. When the first one is finished, SQL Server writes to the second one. Means as a conclusion, SQL Server can be only as fast as your transaction log. When you put your transaction log on a very slow storage, you also have a very slow SQL Server. Okay? The bad thing about auto-growing the transaction log is that SQL Server has to zero initialize the transaction log. Means when you're performing an auto-growth operation, let's say with 1 gigabyte, then SQL Server has to write out 1 gigabyte of zeros. That's always needed for the transaction log, because otherwise the crash recovery process can't know where crash recovery has to stop when a wrap around of the transaction log occurred. With data files, you can suppress that zero initialization by providing the service account under which SQL Server is running the write or the permission perform volume maintenance tasks. But for the transaction log, SQL Server always has to zero initialize that new chunk when the auto-growth happens. There's no way to get rid of that. So what I'm doing now in that demonstration, I'm changing it to SQL Server 2012. And what I'm doing here, I'm creating a terrible database. A terrible, terrible database. I'm specifying an auto-growth factor of 50 gigabytes for the transaction log. I just need some time to look into some specific DMVs, to show you some specific latches. In that case, the auto-growing of the transaction log takes around 7 to 8 seconds, which is still very, very fast. So never ever create such a database in production. In the next step, I'm just creating a table, 2 tables. I begin a new transaction, insert a record, transaction isn't yet committed. In a different transaction or in a different session, I'm adding some additional transaction log records, means my transaction log currently grows or currently fills up. And finally, I'm committing that transaction. Means I have now prepared my transaction log the following. The next insert in that table triggers the outer groove of 50 gigabytes. As you can see with DBCC log info, currently we have just 4 VLFs, means for the next one, for the next insert, SQL Server needs new VLFs, means we trigger the outer groove operation of 50 gigabytes, which takes some time. So we have here that insert, and what I'm trying to show you now is the following. In the first step, not really in the first step, I try to do it concurrently, almost concurrently. We run just 2 insert statements concurrently in 2 different sessions. Means the first one, the highlighted one, triggers the outer groove of the transaction log, 50 gigs, 7 to 8 seconds, and in a second session, I'm trying to insert another record. And that insert will be blocked by the outer groove, by a latch. As soon as SQL Server outer grooves the transaction log, the transaction log is just guarded by a specific latch. And we can see that latch by looking into system exec requests and system OS waiting tasks. So during that blocking situation of 7-8 seconds, I open a third session, and we have here a session ID of 52 and 51. And we just look for both sessions in system exec requests and system OS waiting tasks. So a very complicated thing that I'm trying here, so please no questions in the meantime. I have to mentally prepare me for that thing that I'm trying to do here. Okay, are we ready to go? Yes? Do you want to give me a countdown? Come on. 4, go! Perfect. Takes now a few more seconds, so you can see both sessions are waiting. Outer groove completed. As you can see, it took 9 seconds. When we go to our second insert, it also took around 7 seconds. Let's have a look on system exec requests and system OS waiting tasks. Let's concentrate on system OS waiting tasks because it shows us more information. First session, 51, was the session which triggered the outer groove of the transaction log. In that case, SQL Server calls in the Win32 API API function. Write file gather means we are writing out now 50 gigabytes of zeros. SQL Server reports us here a so-called preemptive wait type, means the SQL OS scheduler has no control over SQL Server anymore. So the SQL OS scheduler doesn't know here how long that preemptive Win32 API call takes. That's a so-called preemptive wait type. Okay, and in addition, we can see our second session, 52, where we tried to do the insert. And that session reports a wait type of latch EX, a non-buffer latch. So we are trying to access one of those 163 shared data structures of SQL Server. In our case, we are trying to access the transaction log for writing out transaction log records, but we can't acquire that latch because that latch is currently acquired by the other thread, which zero initializes our transaction log. And when we go here to the right, you can see which non-buffer latch SQL Server acquired here? A latch called log manager. So we tried to access the transaction log. So we just tried to access a shared data structure in SQL Server like the log manager, and the log manager was currently protected by a latch. Means we can go now to systemOS latch stats to see a breakdown of those latches. So we have here one latch called log manager, and as you can see, we have here a waiting time since our last restart of SQL Server of 15 seconds. I'm well prepared, means I have already tested that. We have a waiting request count of 2. The preparation that I have done previously and the one iteration that we have done here. And on average, we have waited 7.8 seconds on that specific latch on the log manager. Means when you have an existing SQL Server in front of you, you can go to systemOS latch stats and you can check if you have auto-growth operations on the transaction log. Just think about that. The stuff that I'm telling you also makes sense in reality. I'm a funny person. I'm dealing too much with Brandosa. Too much time. Okay? Makes sense? As I'm always saying, SQL Server isn't really a black box. The nice thing about SQL Server is SQL Server provides you a huge amount of information. The bad thing about SQL Server is SQL Server provides you a huge amount of information. Means you have to know where to look and how to interpret all those various information that SQL Server reports back to you. Okay? So therefore, an auto-growth of a transaction log is not really recommended. Of course, because we have done here the auto-growth, we got additional VLFs. So as you can see here, we have here the 4 initial ones that we had, and with such a huge auto-growth factor of 50 gigabytes, SQL Server gives us 16 additional ones. Means that this also leads to a log file fragmentation. The problem of a huge amount of virtual log files is when SQL Server performs the crash recovery process, SQL Server has to go through that linked list. Means the longer the list is, the longer it takes. The recommendation from Microsoft is that you should have a maximum of 50 to 100 virtual log files. With the default configuration of the transaction log of SQL Server, with 1 megabyte and an auto-growth of 10%, you hit that very soon. I have already dealt with customers where cluster failovers took hours. Because when you perform a cluster failover, SQL Server restarts on the different node, means SQL Server has to go through the crash recovery process. They had millions of virtual log files. Therefore, it took hours until that database becomes online. So normally you should not really rely on the auto-growth of the transaction log. Just leave it enabled as a last resort. Normally the transaction log should be as large as your largest transaction. What is your largest transaction? No, it not really depends. Your largest transaction is normally the largest clustered index that you are rebuilding. So when you have a table, let's say with 100 gigabytes, and you rebuild that clustered index, you need at least 100 gigabytes of transaction log. So that's a very easy way to initially size your transaction log. Just look on the largest table inside that database. Question in the back. Perfect. Other questions? No idea on that. Question was autogrowth on system databases. No idea on that, I have to check that. Normally master is very, very small. But MSDB, of course, with the backup, we store history, SQL Server agent jobs and so on. Yeah. But normally you should not really feel it as an end user. Well, you can disable that alert. Very simple. Yeah. 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 So for MSDB, it could make sense to think a little bit more about the transaction log size. Perfect. So we are now finished with latches. Any more questions about latches? It's too late. No, just kidding.
There was a non-buffer latch. So before, with name buffer.
Yeah.
What is that?
The non-buffer latch buffer is the buffer pool in SQL Server. So when we go down, we have here the buffer latch, and that's the buffer pool in SQL Server. Means those are the page latches that we also see in the weight statistics of SQL Server. Yeah, you will also see them in SysTMO as latch stats. Okay. Let's talk now about Spinlocks. Who has already heard about Spinlocks? Who knows what a Spinlock is? Few of you. Perfect. Latches don't scale. Everything that I have told you now about latches is bad because they don't scale. The problem that we have with latches is, as I've already said, every time when we acquire a latch, the query itself goes through that query lifecycle. Means we are in the running state, then we acquire or we try to acquire a specific latch. We can't get that latch, and in that case, the SQLOS scheduler puts that query into the suspended state. Means we are off the CPU, and we are just waiting and waiting and waiting and waiting until we can acquire that latch. Then we have acquired that latch. Afterwards, the SQLOS scheduler moves us into the runnable state, and in the runnable state, we wait until a CPU becomes available, and finally, the scheduler moves us into the running state. And this happens over and over and over and over again. Means we have a huge amount of context switches in the Windows OS, and the whole thing doesn't really scale. Imagine you want to acquire a data structure in SQL Server, and you are just expecting a very, very, very short waiting time. In that case, it doesn't really make sense to go through that query lifecycle. Maybe you're just waiting for a few nano or microseconds. In that case, it doesn't make sense to go from the running to the suspended to the runnable to the running state. It would be more economically and efficiently to stay on the CPU and just spin in a while loop and wait until the resource becomes available. And that's a spin lock. We have now some data structures in SQL Server which are just protected by a spin lock. Means the developers of SQL Server are expecting for that specific data structure a very, very, very short waiting time. And therefore, they have protected that data structure with a spin lock. Means the query tries to acquire that specific spin lock to get access to that data structure. If the spin lock is available, we get it and everything is fine. If the spin lock is currently granted to another thread, then we are still staying on the CPU and we are spinning and we are spinning and waiting actively on the CPU until we can get access to that data structure. It's the same with us people. When we are flying with airplanes, we always expect some waiting times. For example, this week, an airline, I think it's SAS, is striking. So every time when you are flying, you have some waiting times. When you don't want to have waiting times, fly with me. Really, I'm flying for 10, 15 years and I haven't any cancelled flight. I was traveling once in my life with my wife and our flight was cancelled. This was the last time that we have traveled together. So imagine when we are going to an airport, we are traveling by airplane, we are also expecting long waiting times. Means you are preparing for those waiting times, maybe you have some books with you, you are going to the restaurant, eating something, drinking something. Means you are not staying directly at the gate and just waiting and waiting and waiting and waiting. Means you are doing the same that SQL Server is doing with a latch. You're just suspending your waiting time and you are doing something else. The same thing that we have seen with SQL Server, with latches, the query is just put into the suspended state. Some other queries are doing other things in the running state. Imagine you are going to the toilet. On the toilet, we are also expecting some waits sometimes, but only short ones. Who of you goes to the toilet and when the door is locked, goes out for dinner? Nobody. Nobody. Because you are already in an emergency situation, so dinner doesn't make sense anymore. But you get the concept. You're expecting a short wait. Means you're just waiting in the queue, in the line, and you're just actively waiting. You're just waiting until the door is unlocked. Means the door is just a spin lock on which you are waiting on. You get the difference between latches and spin locks? So a spin lock means we have a data structure in front of us and we are just expecting a short waiting time. Okay? A spin lock itself is a so-called mutex. Mutual exclusion means you can have acquired a spin lock or not. Just true or false. Means with a spin lock there are no spin lock types. For example, a shared spin lock, an update spin lock, an exclusive spin lock that we have seen with latches or even with locks in SQL Server. No, it's just a spin lock. You can acquire that. You can have acquired that spin lock or not. Yes or no. Means there is no compatibility. I don't like that word. There's no compatibility matrix, nothing. You can have acquired it, yes or no. Very, very simple. And the spin lock is mainly used by the developers of SQL Server to protect a busy data structure. Means the developers of SQL Server had to define during the development if that specific data structure is a busy one or not. For example, the buffer pool in SQL Server is not really a busy data structure because we have here a latch. The transaction log is also just guarded by a latch and also internally by a Spinlock, because to acquire a latch you also need internally a Spinlock. The problem is now we have some busy data structures in SQL Server, like the lock manager, the hash table in which the lock manager stores all the locks that we have currently granted on our system. And when you have now in such a specific data structure a contention, it can lead to a so-called spin-lock contention. When you are waiting on a latch, you are waiting in the suspended state. Means nothing happens on the CPU. When you are waiting on a spin lock, you are still in the running state on the CPU. Means when you have a spin lock contention, your CPUs are going up to 100%. Very simple. So spin lock contention means now that we are waiting for a longer period of time. The developers of SQL Server thought, hey, that's a busy data structure. We are just expecting very, very short waits. And now we have a very, very long wait. This should normally not really occur. If it occurs, then it's a problem in the design, in the implementation of SQL Server, or maybe you have a bug encountered in SQL Server. And there is one specific bug in SQL Server 2014 RTM, in the lock manager, that we are trying now to reproduce. When we look into the lock manager of SQL Server, the lock manager uses internally a hash table, and the hash table itself consists of multiple hash buckets. When you acquire a lock in SQL Server, that specific lock resource gets hashed, and the result of that hash function defines into which hash bucket SQL Server places that lock. For example, when you are connecting to a database, we always have a shared lock on that database, means nobody else can drop that database, nobody else can restore a backup for that database. In that case, SQL Server hashes the database ID and places the individual shared locks of that database in the same hash bucket. As you can see, when you have here 6 user connections, you have 6 individual shared locks in the same hash bucket. When you want to insert a lock into that hash bucket, then the hash bucket is protected by a spin lock. Means you have to bypass the spin lock. When you have bypassed that spin lock, you can insert at the very end of that linked list your new lock. Means the longer that list gets, the longer it takes until you can insert a shared lock for the same database. And this can lead to a spin lock contention problem. Let's have a look on that. Now it gets really, 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 really nasty. I'm starting here now a .NET application that I have written. I'm not really a good developer, therefore I'm doing consultancy. It's easier. I'm just starting that application, and I show you that code of that application. What I'm doing is very simple and very effective. I'm just opening a SQL connection, and I'm not closing it. And I'm doing that 10,000 times. Means I have in the same hash bucket in the hash table of the lock manager, after a few seconds, 10,000 shared locks. Okay? Let's wait a few more seconds. Take some time. I'm just writing always scrappy code. The question was if a spin lock is very, very important on a NUMA system. Yes, it is important, and normally the spin lock is partitioned across the NUMA nodes, which is not really happening here on SQL Server 2014 RTM. So we have now 10,000 database connections. They are all open, means we have 10,000 shared, whoops, wrong instance. We have now 10,000 shared database locks, as you can see here. Means in that one and only hash bucket, we have now 10,000 shared locks. Means we have a linked list with 10,000 individual locks. Means when you want to insert a new lock into that hash bucket, you have to acquire that spin lock. So the first one enters that critical section, which must be executed single-threaded. I have acquired that spin lock, doing some work, and everyone else has to wait until I release that spin lock. Means the more users you are having, the more spin lock contention you will have. And what I'm doing here now, very simple. I'm using again ostress.exe, and I'm just calling sp reset connection for 100 concurrent users. Means 100 concurrent users are trying to access that specific hash bucket. Let's do that. CPU are up at 100%. And the nice thing is, SQL Server consumes 100%, but the only thing that SQL Server is currently doing is spinning in a while loop. Nothing much, just think about that. On the Enterprise Edition, you are now paying $7,000 for spinning in a while loop per core. Not really effective, a really effective use case of SQL Server. And we have now again statistics about our spin lock, system OS spin lock stats. And we can restrict now on the lock hash spin lock, and you can see we have here so-called backoffs. Means the thread spins and spins and spins and spins and spins, and at some point in time the thread just backs off. I'm giving it up, means I'm just waiting and I'm trying it later. I'm just searching a different toilet. Doesn't make sense to wait any longer in that queue. I'm just backing off. Sorry? No, I'm just going into the suspended state. I'm just giving up. Doesn't make sense anymore. Means in that case, the backoffs are just going up and up and up and up and up, as you can see. They're just going up. You can further troubleshoot that. Of course, when you don't know in which spin lock you have a contention, just make an order by backoffs descending. Now we know we have a contention in the lock hash spin lock. Now we can work with extended events. And we can create an extended event session which captures the backoff events for that specific spin lock type. So we need to retrieve the internal ID of the lock hash spin lock, which is 129. And in the next step, we can create a simple event session, and we capture the event spin lock backoff from the package SQLOS. We capture the call stack, the C++ call stack, not the DSQL call stack. And we just restrict on that specific spin lock type. Never ever run that event session without a predicate, because backoffs are always occurring. We are now only interested in the lock hash spin lock. And we write everything into the histogram, and we just making a group by aggregation on the call stack, on the C++ call stack. So we just want to know in which C++ call stack we have the largest amount of backoffs events. I have also installed here in my VM the public symbols of SQL Server. They're also somewhere here. You can also download them. There's a blog posting from Paul Randall which describes how that works. So let's see, I have here for example SQLlang, which implements something about SQL Server. So we need some specific trace flags. When we enable those trace flags, the extended event session will also symbolize the C++ call stack for us, so we see which function calls we have the contention in SQL Server. And now we start it. So we have here on the left-hand side our event sessions, and we have here the histogram. And as you can see here, we have here the first one, the first call stack, where our backoff events are going up and up. 23,000 times, 37,000 times. And the first column gives you the C++ call stack. I've already copied that call stack out for you. So when we go back here, I have here that call stack. I make that larger. And as you can see, that's just C++. So we are executing here a SQLOS task. We have a login useDB helper where we use our database with a specific ID. Then we open that database, and we want to get a shared database lock from the lock manager. And you can see here that we go to that spin lock ID 129. We don't get the spin lock, and we acquire with an exponential backoff, means we are going sleeping, and finally our X event session kicks in. So with the public symbols and with such an event session, you can also find out in which regions of SQL Server you have spin lock contention. Of course, you have to interpret that. That's the hard part about it. So that's one demonstration, one demo that I got from Bob Ward. Bob Ward was kind enough to share that with me, because normally for us, we have no idea what happens here. Okay? As you can see, CPUs are still up, so let's close that to get control for our server. Of course, you are telling me now, okay, Spinlock contention with just 4 cores, come on. That's nothing, no problem. I have here another virtual machine with 32 cores, running on the new version of Apple iPhone. No, just kidding, that's an Amazon EC2 instance that I'm running. 32 cores, 244 gigabytes of RAM. As I've already twittered a few hours ago, that's the most expensive SQL Server session that I'm doing here. Because that VM is already running for 3 hours and I'm paying here some money for that. For such a huge VM. So I just want to show you the same thing again. I have already opened, hopefully, yeah, I have already opened my dirtywritten.net application. So we have already our 10,000 shared database logs, or not? No? Oh. Let's restart it. This is a little bit faster on a larger system. As you will see, the same thing will happen. Our CPUs, all 32s, are just going to 100%, and the backup events in that log hash spin log, they are just exploding. They are just exploding because we have so many threads which are spinning actively on the CPU. They are just exploding. 8,000. So we see we have some. And now we are going to ostress.exe and we're just running the same thing again. So as you can see, immediately all our CPUs are going up to almost 100%. This means the more CPUs you have, the crazier Spinlock contention gets. Just think about that. When you have a system with 256 cores, all your 256 cores are just spinning in a while loop. Doesn't matter. The more cores you are having, the more cores are spinning. And as you can see, when we are going to the Spinlock stats, the backoffs are just exploding. We have here 1.7 millions. When we execute that again, I have already 1.8 millions. Of course, the more cores you have, the more backoff events will occur. Okay? So normally, it's so nice to see. It's so nice to see SQL Server doing useless work, just spinning in a simple while loop. Normally, when you see such a thing, SQL Server is running at almost 100%, and SQL Server isn't performing any work, then you have Spinlock contention. If SQL Server is doing something usefulness in the background, okay, maybe you have other problems with your indexing strategy and you have expensive clustered index scan sort operations in your execution plans, or bad statistics which are driving some execution plans crazy with bookmark lookups and something. But when you see a CPU consumption at 100%, and SQL Server isn't doing any useful work, please check your Spinlock stats. Okay? Yeah? Then we still, question was, what happens if we can't log into SQL Server? Then we just use the backdoor dedicated admin connection, because with the dedicated admin connection, SQL Server always preserves your SQLOS scheduler and also a dedicated memory node. Means as long as SQL Server is online and running, you are able to connect to SQL Server. That's just the backdoor into SQL Server. Question? Yeah, I've heard that yesterday in Brent's Precon, yeah. Mm-hmm. Yeah. Yeah. Yeah, as I've already said here, this also only works on the RTM version of SQL Server 2014. Yeah. So in a subsequent CU, they have fixed that specific problem by partitioning the log manager's hash table across multiple NUMA nodes. Yeah. Yeah. So mainly it's just a bug in SQL Server that we see here, but only in the RTM version. Okay. Yeah. By design, and we don't fix it, so it's a bug. Okay. Let's shut that one down. Okay. We have 15 more minutes. Any questions about Spinlocks? Mm-hmm. Yeah. So the question was if you can do anything about spin-lock contention. Sometimes yes. At first you have to know where that contention occurs, like in the log hash manager. Then you have to find out which queries are causing that spin lock contention. For example, a few years ago I had one customer in the UK and they also have triggered a spin lock contention in the log hash spin lock. They were running a very, very large deployment based on service broker, and they had one stored procedure, an activated one, which processed messages, and inside that stored procedure they had a simple select statement which retrieved some configuration values from a configuration table. And that stored procedure was executed hundreds, thousands of times every second. They have finally forgotten to commit some transactions, so also some crappy code. And we have identified that specific stored procedure as the root cause of spin lock contention, and the change was easy. Select from that table with no log. It was just a static configuration table, so no dirty reads. Normally, when you have problems with spin locks, something terrible happens within SQL Server because you're already fighting against SQL Server. As I've said earlier, with a spin lock, Microsoft assumes that we just have a short waiting time. And we are just violating with some specific kind of code that assumption. It's the same as we have seen previously with latches. Last page insert latch contention, you are already fighting against the B-tree structure. You're already fighting against the underlying data structure that SQL Server uses internally to represent our data. So when you have identified the root cause of the spin lock contention and you have identified that shared resource where that contention is, sometimes it's easy to solve it. For example, as I've said, with the log hash manager spin lock, use a no log, just bypass it. Very simple. Okay. In the few remaining minutes, I want to talk a little bit more about log-free data structures. Who of you has already heard about in-memory OLTP? Who thinks that in-memory OLTP solves problems? Who thinks that in-memory OLTP generate problems? Yeah. Come on. Normally, I will say that there are not really any use cases currently where in-memory OLTP makes too much sense. It's a very specialized technology that Microsoft provides us, and it's just a version 1. You can't do almost nothing with that thing. For example, you have no support for foreign keys. You can't truncate a table. You can't change a table. You can't change your indexing strategy. So not really useful currently. And in-memory OLTP hackathon is based on the principles of lock-free data structures, means everything in in-memory OLTP is without locking, without latching, without spin locking. Means we are not waiting anymore on anything, as long as we are working in our in-memory OLTP world. Means with in-memory OLTP you can create memory optimized tables, you can create native compiled stored procedures, as long as you are working with those constructs in SQL Server. Everything is lock and latch and spin lock free. Everything else in SQL Server is the old crappy code that we have seen so far. And the idea behind lock-free data structures is that we implement a so-called non-blocking algorithm. Wikipedia has a nice definition. I don't want to read everything about that definition, just the last sentence. A non-blocking algorithm is lock-free if there is guaranteed system-wide progress regardless of the thread scheduling. Let's have a look on that, what it means. This is now a SQL Server session and I'm showing you C++ code. Yeah. You don't need to understand that code that we see here. That's just a code that shows on a very high level view how a spin lock is implemented. In reality, it's much more complex. Much more complex. When you implement in that way a spin lock, it will not work in any way. The idea behind a spin lock is that we have a so-called critical section. A critical section is just a code path in a C++ code that we want to execute single-threaded. As we have seen earlier, when we have accessed a specific hash bucket in the hash table of the lock manager, then SQL Server also had a critical section, a code path that was guarded by a spin lock. And as you can see here, when we work with spin locks, a spin lock is internally implemented with one specific assembler instruction, compare exchange. Means we have here a function compare and swap, and normally this function is just one assembly opcode. And the goal here is that you have a shared variable. You are comparing that variable against an expected value. If you have that expected value, then you set a new value, otherwise you're returning the old value. Means, as you can see here, we have our while loop, where we are spinning. We are just spinning in the while loop, we are calling compare and swap, and we are waiting until our variable lock has the value unlocked. For example, the value 0, false. If that variable has the value 0, then we set that variable to locked. For example, the value of 1 means we have acquired that spin lock and all the other threads are just stuck in that while loop. And at the very end, when we are leaving our critical section, we just unlock that spin lock, means someone else can acquire that spin lock. That's a simple, naive implementation of a spin lock. The problem is, when you have here a thread which acquires that spin lock, and sometimes that thread gets suspended, you have a huge problem. Because the other ones are just spinning in that while loop forever. Means that implementation is not a non-blocking algorithm because one thread has influence on the thread scheduling of the other ones. Okay? So that's just a traditional way how SQL Server implements internally Spinlocks. As you can see, we have here inside that critical section a code which just wants to increment a shared variable by a value of 5. You can also rewrite that code with a non-blocking algorithm. As you can see here, we have again our while loop. But what we are doing here is the following. We are just looping and we are just checking if someone has changed that value in the meantime. So we are just working optimistically, like optimistic concurrency in SQL Server. We are just checking in the while loop if someone has changed that value. If not, we are making our atomic addition. And if not, we're just retrying it over and over and over again. Means we have here no shared resources incorporated anymore. Means when one thread gets suspended, it hasn't any influence on other threads. Means the individual threads can progress individually from each other. That's very, very important that we have here no shared resources that are coordinated. And that's just the technique that is used by in-memory OLTP internally. So instead of acquiring Spinlocks, everything in in-memory OLTP is just optimistic. For example, when we have two transactions, both transactions can run concurrently in an optimistic way, and at the very end, we go into a validation phase, and in that validation phase, in-memory OLTP just checks if we can consistently commit that transaction. So for example, you can concurrently make an insert with the same primary key value into a memory optimized table. You can commit both transactions, but at the very end, one transaction will commit and the other one will be rolled back. Just optimistic concurrency. We always start our transactions under the assumptions that our transactions will succeed. And now, I just want to show you a few more examples how we can work with in-memory OLTP. We have talked earlier about the last page insert latch contention. We have seen a few ways how we can overcome that. Unique identifier, random clustered key value. We can bed our record so that every record just fits onto one page. We can use a hash partitioning in the expansive edition of SQL Server. So just different ways how to deal with that specific problem. In-memory OLTP can be also a way how to resolve that problem, because in-memory OLTP doesn't know anything about latches, doesn't know anything about Spinlocks. There are no latches, there are no Spinlocks. Means there can't be any latch contention, because we have no latches. So I'm just preparing that database for in-memory OLTP. Means I'm adding a memory optimized file group to that table, to that database, and I'm adding a new container. And now I create a memory optimized table. It's a traditional SQL Server table with a huge amount of restrictions. Specifying here primary key constraint. The primary key constraint is enforced with a non-clustered hash index, and we tell SQL Server we want to create a memory optimized table. In that case, SQL Server generates for that table C code. That C code is compiled to a DLL file, and the DLL file was loaded into the process space of SQL Server.exe. So when we created that table, magic has happened inside SQL Server, real magic. I create a traditional interpreted stored procedure. And again, we're just inserting 10,000 rows. The same thing that we wanted to do previously with our unique identifier clustered key value. And I'm executing again that stored procedure. Previously, with the unique identifier value, we had an execution time, I think it was around 6 seconds. Okay, 6 seconds. Now we have a memory optimized table, no locking, no latching, no spin locking, nothing. Let's try to execute it. And let's see how fast or how slow it is. Takes a few seconds, not too long. 3 seconds. Improvement by 100%. Hackathon was the code name. Hackathon is a Greek word and means 100. The goal of hackathon of in-memory OLTP is an improvement of 100x. Not 100%, 100x. Instead of 100 seconds, your workload should take 1 second. Just think about that. Here, with the memory optimized table, we had just an improvement of 2x, 100%. Not too much. But again, already great. But we have called an interpreted stored procedure. Means all the stored procedures that we are executing over the last years are really, really slow in SQL Server because they are just interpreted during runtime. Interpretation means you need a huge amount of clock cycles, a huge amount of CPU instructions. So you're just wasting a huge amount of clock cycles for all your cores that you are licensing very, very expensive. And for that case, in-memory OLTP provides us the possibility to natively compile a stored procedure. Means the definition of that stored procedure is compiled down to C code. The C code is linked to a DLL file, and the DLL file is loaded again into the process space of SQL Server. Means when you execute your stored procedure, you just execute assembly code, optimized assembly code. So what I'm doing here, again, I can prove we have 1 million of records. So I'm not fooling you here in any way. 1 million of records. And now let's have a look on the weight stats. What do you mean? How much page latches we have here? 0. Very simple. There are no latches. Okay? There's no latching, nothing. We've just written to the transaction log. And even the transaction log writes can be deferred by using delayed transactions. Means you are writing out to the transaction log asynchronously. Means you can lose data. Not really recommended, but it's fast. Let's drop that stored procedure and let's recreate that stored procedure with native compilation. A stored procedure with native compilation must be always created as schema binding. Means you can't change the underlying table. Doesn't matter for in-memory OLTP because your table can't be changed in any way. You have to specify your security context, execute as, because the security checks are coded into the generated C code. Just think about that. With an atomic block, you have to specify your transaction isolation level, and you have to specify your language. Because in-memory OLTP needs to know the language in which you want to have error messages. We are just compiling here native machine code, nothing more. Again, 10,000 inserts in a simple while loop. We don't need to clear our weight stats. We don't have weights here anymore. And I'm running that stored procedure again. Finished. Just think about that. 938 milliseconds. There's no latching, no blocking, no spin locking. We're just executing native machine code. So you can do really, really, really amazing things within memory OLTP. At the beginning of the session, we have started with the same table, with the same workload, and it took 1 minute 33 seconds. Now we are just talking about 938 milliseconds. Just think about that. But again, in-memory OLTP has a huge amount of drawbacks. You can't change your table anymore. You have to swap your table. Oops, when I'm swapping my table, I'm losing my data. So you have to move your data somewhere else. Microsoft recommends you need the double amount of RAM as you have data in your table. So as Brent has said yesterday, imagine we have a table with 100 gigs. We need 200 gigabytes of RAM just for the in-memory stuff. When we move that data to a different table, you need 200 gigabytes again. Just 400 gigabytes for a simple table. You can't truncate the table. You can't create foreign keys. So a huge amount of drawbacks. The same with native compilation. You have no parameter sniffing. Every values are just treated as unknown values, means it depends on the selectivity of your data. You have no recompilations, you have no execution plan. And everything executes so fast that you can't do any performance troubleshooting with the DMVs because they are in milliseconds. Who cares about milliseconds when we're executing assembly instructions in nanoseconds? Okay. And again, I have not fooled you. We have now in that table 2 million of rows. And again, we have no weights. There can't be any weights because we're not waiting anymore. We're just doing everything optimistically. Questions? Perfect. We are at the end. After almost 2.5 hours. Nice. I can talk forever. So what we have seen, we have started by talking about latches. As I've said, a latch means that the query goes through the whole query lifecycle, means we're expecting a longer wait, like when we're going to the airport and our flight is delayed. Then we moved on to Spinlocks. A Spinlock just expects a very, very short wait, means it's a busy wait. We're just waiting actively in a while loop directly on our CPU. As you have seen, it's very easy to get under different SQL Server builds into Spinlock contention. The most prominent Spinlock contention is within the log hash manager. That's the easiest one to reproduce, for example, on the RTM version of SQL Server 2014. And at the very end, I have talked a little bit more about in-memory OLTP, log-free data structures. And as you have seen, you can have a amazingly fast performance with a huge amount of drawbacks. If you want to know more about SQL Server, I'm running my SQL Server performance tuning and troubleshooting workshop in London, first week of June, 5 days, with a huge amount of SQL Server topics, ranging from execution plans, index tuning, locking, blocking, deadlocking, extended events, our public toilet of SQL Server, performance monitoring, troubleshooting, just everything that you need to know about SQL Server. If you give me a business card today or even tomorrow, I can also give you a discount of 10%, or just send me an email that you have attended my great session at the SQLRally conference. Okay. Thanks for attending. I hope that you have enjoyed that session. I will also block the whole content about that session, so in a few days you will find slide samples, everything for download on my website at sqlpassion.at. So thanks again for attending and enjoy the remaining day at the bar. Thank you.